Welcome to this walkthrough of LeetCode number 1288, Remove Covered Intervals. In this problem, we'll explore how to efficiently determine the number of intervals that remain after removing those fully covered by others. Let's dive into the problem, break it down step by step, and find an optimal solution. In this problem, you're given a list of intervals, where each interval is represented as a pair, L_I, R_I. These pairs define the start and end points of the interval, and since the intervals are closed, both endpoints are included. The goal is to identify and remove intervals that are completely covered by another interval in the list. An interval, a, b, is considered covered by another interval, c, d, if the starting point a is greater than or equal to c, and the ending point b is less than or equal to d. In simpler terms, one interval is covered if it lies entirely within the boundaries of another. Once you have removed all the covered intervals, you need to return the count of intervals that remain. The input consists of a list of these intervals, and you can assume that the start of each interval is less than or equal to its end. The output will be the total number of intervals left after removing the covered ones. Let's look at an example to understand this better. Suppose the input intervals are 1, 4, 3, 6, 2, 8. The output in this case would be 2. Here's why: the interval 1, 4 is covered by 2, 8, because 2 is less than or equal to 1, and 4 is less than or equal to 8. Similarly, the interval 3, 6 is also covered by 2, 8, for the same reason its boundaries lie completely within 2, 8. This leaves us with only the interval 2, 8 as one of the remaining intervals. Additionally, since no other interval can cover 2, 8, it stays in the list. Therefore, after removing the covered intervals, two intervals remain, 2, 8, and 3, 6, giving a result of 2. Now consider another example where the input is 1, 4, 2, 3. The output here is 1. In this case, the interval 2, 3 is covered by 1, 4, because 1 is less than or equal to 2, and 3 is less than or equal to 4. This means 2, 3 lies entirely within the boundaries of 1, 4. As a result, only the interval 1, 4 remains after removing the covered intervals. Since no other intervals are left, the final count is 1. This example highlights how intervals with smaller ranges can be removed when they are completely contained within a larger one. In a third example, the input intervals are 1, 2, 1, 4, 3, 4. Here, the output is 2. Let's break it down. The interval 1, 2 is not covered by any other interval because no single interval fully contains both 1 and 2. Similarly, 3, 4 is not covered by any other interval in the list for the same reason: it doesn't fall completely within the boundaries of another interval. Lastly, 1, 4 is also not covered by any other interval. Since no intervals are removed in this case, the intervals 1, 4 and 3, 4 remain, giving us a result of 2. Finally, let's go over some constraints and edge cases. The number of intervals can range from 1 to 1000, and each interval will always have two elements. The start and end points of each interval will fall between 0 and 10,000, and all intervals in the input are distinct. One edge case to consider is when there is only a single interval, such as 2, 3. Here, there are no other intervals to cover it, so the output is 1. Another edge case is when all intervals overlap, like 1, 10, 2, 9, 3, 8. In this case, only the largest interval, 1, 10, remains, giving an output of 1. Similarly, if no intervals cover each other, as in 1, 2, 3, 4, 5, 6, all intervals remain, and the output is the total number of intervals, which is 3. Lastly, if multiple intervals share the same endpoint, such as 1, 4, 2, 4, 3, 4, the largest interval, 1, 4, is the only one that remains, resulting in an output of 1. To tackle the problem of removing covered intervals, we first need to understand the concept of coverage. For any two intervals, say a equals L1, R1, and b equals L2, R2, we say that A is covered by B if the starting point of B is less than or equal to the starting point of A and the ending point of B is greater than or equal to the ending point of A. One straightforward way to solve this is the brute force approach, where we compare every pair of intervals to check if one is covered by another. This means iterating through all combinations of intervals, marking any covered intervals for removal. However, this method has a time complexity of n squared, due to the nested iterations, making it inefficient for large datasets. It also requires careful handling to avoid potential errors when removing intervals during iteration. While simple to understand, the brute force approach is not practical for larger inputs due to its inefficiency. A more efficient solution is the optimized sorting approach. Here, we first sort the intervals by their starting points. If two intervals share the same starting point, we sort them further by their ending points in descending order. This ensures that intervals with broader coverage come earlier in the order. Once sorted, we iterate through the intervals while maintaining a variable, max_end, to track the farthest endpoint encountered so far. For each interval, we check if its endpoint is less than or equal to max_end. If it is, the interval is covered and can be ignored. Otherwise, we increment the count of remaining intervals and update max_end to the current interval's endpoint. This approach is efficient because sorting the intervals takes n log n, and the subsequent single pass through the list is n. It avoids unnecessary comparisons and is much faster than brute force, especially for larger inputs. While there are alternative methods, such as using a sweepline algorithm, these can be more complex to implement and are less intuitive for this problem. After evaluating the options, we selected the optimized sorting approach as the most balanced solution in terms of clarity, efficiency, and simplicity. The key insight here is that sorting intervals by their start points, and by their end points in descending order for ties, allows us to process them in a way that simplifies the coverage check. By tracking just one variable, max_end, we can efficiently determine whether an interval is covered without needing additional data structures or nested loops. This approach reduces the complexity from n squared in the brute force method to n log n, thanks to the sorting step. While sweepline methods are an alternative, they introduce unnecessary complexity for this specific problem. The simplicity and scalability of the optimized sorting approach make it the ideal choice. It not only ensures correctness but also keeps the implementation straightforward, making it practical for competitive programming and real-world applications alike. The problem remove covered intervals asks us to determine how many intervals remain uncovered after identifying and removing those that are completely contained within another interval. An interval, a, b, is considered covered by c, d if c, d starts at or before a, b, and ends at or after it. To solve this, the first step is sorting the intervals. Sorting is a key strategy because it allows us to process intervals sequentially, making it easier to determine relationships between them. Specifically, we sort intervals by their starting points in ascending order. If two intervals share the same starting point, we further sort them by their ending points in descending order. This ensures that, for intervals with the same start, the longer one appears first. This sorting order is crucial because it simplifies the process of identifying which intervals are covered. By arranging intervals this way, we can evaluate them efficiently in a single pass. Once the intervals are sorted, we initialize two variables to help with the computation. The first variable, max_end, will keep track of the farthest endpoint encountered so far as we process the intervals. The second variable, remaining_intervals, will count the number of intervals that are not covered. Now, we iterate over the sorted intervals one by one. For each interval, we compare its endpoint with max_end. If the current interval's endpoint is less than or equal to max_end, it means this interval is covered by a previously processed interval, so we skip it. Otherwise, we update max_end to the current interval's endpoint and increment the count of remaining intervals. This approach works because the sorting ensures that intervals are processed in a way that allows us to identify coverage using only the max_end variable. By the end of the iteration, remaining intervals will contain the count of all intervals that are not covered by any other. The algorithm uses the sorted list of intervals as input and produces an integer as output, representing the number of non-covered intervals. This efficiency is achieved because sorting the intervals ensures that we only need one variable, max_end, to manage the relationships between intervals. This eliminates the need for additional data structures, keeping the space complexity optimized. When analyzing the algorithm's complexity, we see that sorting the intervals takes n log n time, where n is the number of intervals. The subsequent single pass through the intervals to determine coverage takes n time. Combining these, the overall time complexity of the solution is O, n log n. In terms of space complexity, since the sorting can be done in place and no extra space beyond a few variables is used, the additional space complexity is O, 1. This makes the algorithm both time efficient and space efficient, well suited for handling large inputs. Let's go through an example to solidify the concept. Suppose the input is 1, 4, 3, 6, 2, 8. First, we sort the intervals by their starting points, and for intervals with the same start, by their ending points in descending order. This gives us the sorted list 1, 4, 2, 8, 3, 6. Next, we initialize max_n to 0 and remaining underscore intervals to 0. Now we iterate through the intervals. For the first interval, 1, 4, its endpoint 4 is greater than max_n, so we update max_n to 4 and increment remaining underscore intervals to 1. For the second interval, 2, 8, its endpoint 8 is greater than the current max_n of 4, so we update max_n to 8 and increment remaining underscore intervals to 2. For the third interval, 3, 6, its endpoint 6 is less than or equal to max_n, so we skip this interval. The final count of remaining underscore intervals is 2, which is our output. This approach also handles edge cases effectively, such as when there's only one interval, when all intervals are covered, when no intervals are covered, or when intervals are identical. Each of these scenarios is handled naturally by the algorithm's logic, ensuring correctness in all cases. This Python implementation solves LeetCode problem number 1288, remove covered intervals. The goal is to determine how many intervals remain after removing those covered by others. An interval, a, b, is covered by c, d, if c equals a and b equals d. The algorithm begins by sorting the intervals. Sorting is done first by the start points in ascending order and, in case of a tie, by the end points in descending order. This ensures that intervals likely to cover others are grouped together, making subsequent comparisons straightforward. We initialize two variables, max_n, to track the farthest end point seen so far, and count, to keep track of the number of non-covered intervals. Both are initially set to 0. Next, we iterate through the sorted intervals. For each interval, we check whether its endpoint is greater than max_n. This condition indicates that the current interval is not covered by any previous interval. If true, we increment the count and update max_n to the current interval's end. The final value of count represents the number of intervals that remain after removing all covered intervals. This solution is efficient, with a time complexity of O, n log n, due to sorting, followed by an O, n, iteration through the intervals. The space complexity is O, 1, as no additional memory is used beyond a few variables. This is the Java implementation for LeetCode problem number 1288, remove covered intervals. The solution mirrors the Python logic provided, using Java-specific features such as the arrays.sort method with a custom comparator for sorting intervals. The algorithm sorts intervals first by their start points, and in the case of ties, by their end points in descending order. It then iterates through the sorted intervals to count the non-covered intervals while maintaining the maximum endpoint encountered so far. This implementation demonstrates efficient handling of the problem using Java's collections and type system. We start with the first example, where the input intervals are 1, 4, 3, 6, 2, 8. The first step is to sort these intervals. Sorting is done by the start point in ascending order, and if two intervals happen to have the same start, we sort them by the endpoint in descending order. After applying this sorting rule, the intervals become 1, 4, 2, 8, 3, 6. Next, we initialize two variables, max_n, which is set to 0 to keep track of the largest endpoint we've seen so far, and count, which starts at 0 and will store the number of non-covered intervals. Now, we iterate through each interval. The first interval is 1, 4. Its endpoint, 4, is greater than max_n, which is currently 0. This means 1, 4, is not covered by any previous interval. So, we increase count to 1 and update max_n to 4. Moving to the next interval, 2, 8, its endpoint, 8, is greater than the current max_n of 4. This means 2, 8, is also not covered. We increment count to 2 and update max_n to 8. Finally, 4, 3, 6, its endpoint, 6, is less than max_end, which is 8. This means 3, 6 is covered, so we don't make any changes to count or max_end. The final output for this example is 2, as there are two non-covered intervals. Now let's consider a second example where all intervals are non-covered. The input is 1, 2, 3, 4, 5, 6. Again, we start by sorting the intervals. Since they are already sorted by start points in ascending order, no changes are needed, and the sorted intervals remain 1, 2, 3, 4, 5, 6. We initialize max_end to 0 and count to 0 as before. Starting the iteration, the first interval is 1, 2. Its endpoint, 2, is greater than max_end, which is 0. This means 1, 2 is not covered, so we increment count to 1 and update max_end to 2. For the next interval, 3, 4, its endpoint, 4, is greater than the current max_end of 2. This means 3, 4 is also not covered. We increment count to 2 and update max_end to 4. Finally, for the interval 5, 6, its endpoint, 6, is greater than the current max_end of 4. This means 5, 6 is not covered either. We update count to 3 and max_end to 6. Since all intervals in this example are non-covered, the final output is 3. Now consider a third example where all intervals are covered. The input is 1, 10, 2, 5, 3, 7. After sorting, the intervals remain the same 1, 10, 2, 5, 3, 7. We initialize max_end to 0 and count to 0 as usual. Starting with the first interval, 1, 10, its endpoint, 10, is greater than max_end, which is 0. This means 1, 10 is not covered. We increment count to 1 and set max_end to 10. Next, for the interval 2, 5, its endpoint, 5, is less than max_end, which is now 10. This indicates that 2, 5 is covered by 1, 10. Therefore, we make no changes to count or max_end. Similarly, for the interval 3, 7, its endpoint, 7, is also less than max_end, which is still 10. This means 3, 7 is also covered. Again, no changes are made to count or max_end. At the end of this process, only one interval, 1, 10, is non-covered, so the final output is 1. To understand the time complexity of this solution, we can break it into two main steps, sorting the intervals and iterating over them. First, when we sort the intervals, Python's sort function uses timsort, which has a time complexity of n*log n. This is because sorting involves comparing the start and end points of the intervals, and with n intervals, the sorting step is the most computationally expensive. Then, after sorting, the algorithm iterates through the intervals using a single loop. In each iteration, it performs constant time operations, such as comparing the current interval's endpoint with the maximum endpoint seen so far and updating variables. With n intervals, this iteration contributes n to the time complexity. When we combine these two steps, the total time complexity becomes n*log n plus n, which simplifies to n*log n. Since the sorting step dominates, this is the final time complexity of the solution. Now, looking at the space complexity, we start by considering the input storage. The input list intervals itself requires n space because it holds n intervals. Next, the sorting operation introduces some overhead. Python's timsort algorithm, which is used for the sorted function, has a worst-case space complexity of n. Additionally, the algorithm uses two scalar variables, max_end and count, to track the maximum endpoint and the count of non-covered intervals. Since these variables are independent of the input size, they only require 1 space. Combining these factors, the overall space complexity is dominated by the input storage and sorting overhead, both of which are n. Therefore, the final space complexity of the solution is n. When comparing this optimized approach to a brute force solution, the differences become clear. The naive approach involves comparing each interval with every other interval to determine if it is covered. This requires a nested loop, where the outer loop iterates over all n intervals, and the inner loop performs n comparisons for each interval. This results in a time complexity of O(n) squared. On the other hand, the space complexity of the brute force approach remains O(n), as no additional data structures are used beyond the input. In contrast, the optimized solution significantly reduces the time complexity by leveraging sorting. Sorting the intervals ensures that only adjacent intervals need to be checked for coverage, reducing the time complexity to O(n*log n). The space complexity remains O(n) in both approaches, but the optimized solution is far more efficient in terms of time, making it the better choice for large input sizes. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, the sorting step still requires O(n*log n), as the time complexity of sorting is independent of the input configuration. Similarly, in the average case, sorting dominates with O(n*log n) complexity, and the iteration step adds O(n). This makes the average case time complexity O(n*log n) as well. In the worst case, even with the most complex input distribution, sorting remains the dominant factor, resulting in a worst-case time complexity of O(n*log n). The space complexity, on the other hand, is O(n) across all cases, as it depends only on the input size and the sorting algorithm's overhead, which is linear in the worst case. This analysis confirms that sorting is the primary contributor to the time complexity, while the overall space complexity remains optimal at O(n). One common mistake in solving the remove covered intervals problem is sorting the intervals incorrectly. A frequent error is sorting them only by their start points, which can fail when intervals overlap partially. For instance, if we have intervals 1, 4, and 1, 3, sorting only by start points will not account for the fact that 1, 4 fully covers 1, 3. The correct method is to sort by start points first and then by endpoints in descending order. This ensures that the interval with the larger end is considered first, making it easier to identify covered intervals. Another common pitfall is neglecting edge cases, like assuming all intervals are unique or presorted. Overlooking scenarios such as a single interval, identical intervals, or even intervals with zero length can cause runtime errors or incorrect results. To avoid this, make sure to explicitly test these edge cases, such as 1, 2, 1, 4, 1, 4, or 1, 1. These steps can save you from subtle bugs and ensure your solution is robust. Another frequent error is comparing intervals incorrectly. Many solutions fail because they use simple greater than or less than operators without considering inclusive bounds. Remember, coverage includes equality at the boundaries, so improper comparisons can lead to removing intervals that aren't actually covered. The fix here is to use greater than or equal to and less than or equal to operators when comparing endpoints. Additionally, using nested loops to compare every pair of intervals is another mistake to avoid. While it may seem straightforward, this brute force approach has a time complexity of O(n squared, which becomes impractical for large inputs, such as when n reaches 10,000. Instead, sorting the intervals and using a greedy approach with a single traversal achieves a more efficient O(n)log n solution. Lastly, it's critical to properly update the variable that tracks the end of the last interval, often called last_end. Forgetting to update it or doing so incorrectly can lead to errors like skipping valid intervals or wrongly removing others. Always ensure that last_end is updated only when an interval is not covered by the current one. To succeed in interviews, it's important to understand the key insights behind the problem. Sorting the intervals by start point in ascending order and by end point in descending order is not just a technical detail, it's crucial for simplifying the process of identifying covered intervals. This problem also exemplifies the greedy algorithm pattern, where we make the best decision locally, removing covered intervals, to arrive at the optimal global solution. During interviews, it's helpful to discuss the trade-offs between a brute force O(n squared solution and the more efficient O(n)log n sorting approach. This shows that you understand not only the solution but also why it's the best choice for large datasets. Additionally, always test and mention edge cases. Scenarios like a single interval, duplicate intervals, or intervals with zero length often come up, and demonstrating your awareness of these edge cases can set you apart as a strong problem solver. Lastly, be ready for follow-up questions. For example, the interviewer might ask you to extend the solution to related problems, such as merging intervals, as seen in LeetCode number 56, or finding maximum overlapping intervals. This problem shares similarities with several other interval-related problems that you might encounter. For example, LeetCode number 56, merge intervals, focuses on combining overlapping intervals into a single merged interval. LeetCode number 435, non-overlapping intervals, is about removing the minimum number of intervals to ensure the rest are non-overlapping. LeetCode number 252, meeting rooms, involves determining if a person can attend all meetings without scheduling conflicts, while LeetCode number 253, meeting rooms 2, calculates the minimum number of meeting rooms required for overlapping meetings. These problems often share concepts like sorting and interval comparisons, so familiarity with them can strengthen your understanding of interval-based algorithms. Another variation to consider is the brute force approach for removing covered intervals. This involves comparing every pair of intervals to check if one is covered by another. While this method is simple to implement, it has a time complexity of n squared, making it inefficient for large inputs. Understanding these related problems and alternatives helps you build a broader perspective on interval-based challenges. For an optimized solution, sorting combined with a greedy approach is the way to go. By sorting intervals by their start points in ascending order and their end points in descending order, you can ensure that covered intervals are easier to identify. Once sorted, a single traversal of the intervals allows you to track the last _end variable, which helps determine which intervals are covered. This approach has a time complexity of n log n due to sorting, making it much more efficient than brute force for larger datasets. However, it requires a good understanding of both sorting mechanics and greedy algorithms. For more advanced scenarios, you could explore using data structures like segment trees or binary index trees. These structures allow for dynamically tracking interval coverage, which could be useful for variations of this problem involving dynamic updates or queries. While these methods also have a complexity of n log n for preprocessing, they introduce additional complexity in implementation and are generally overkill for the static input in this problem. By mastering the optimized approach, you'll be equipped to handle this problem efficiently and extend your knowledge to other variations. Great job working through this problem. To summarize, we use sorting and careful iteration to identify and remove covered intervals efficiently. Remember the importance of handling edge cases and applying sorting techniques to interval problems. Thanks for watching, and I'll see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!